So welcome to this virtual 3D experience e-internship program, day 5. And I am Samesh Balaji. I am basically an mechanical engineer and PG in thermal power engineering. So I have 10 plus years of experience and I am with EDS Technologies for past 8 years. And I take care of pre-sales and post-sales. So let's have a recap of day 4, what we learned up to day 4. So we learned how to create 2D sketches on the platform and then how to convert them into 3D models and how to create complex shapes and also how to assemble. Now, once you do the assembly in digital format, what happens is that the clearances or if there is any penetration, those things will not be considered. But when it comes to manufacturing, those things are very important. So that is why you have something known as 3D GD&T, which is known as geometric dimensioning and tolerancing. Once you complete this GD&T stage, you enter into 2D drafting where the drawing goes to the manufacturing floor where engineer will be able to understand and then they will set up the rest of the manufacturing process. And we have considered drone as the example here, or it could be any stuff. Let's say it could be a four-wheeler or it could be an aircraft. Anything you consider, it also has this electrical component. It's nothing but the wiring and the electronics. So even that is taken care in the electrical wire harness. Then comes the weight management, where we always try to keep in mind that weight is always reduced with more stiffness. Then there's an option or stage where you can do the digital mock-up validation, where let's say if you design an engine, then you can make the engine run in the software and then understand where is the clash happening or is there any constraint to be removed or whatever it is. Anything which you want to refine, that can be done in the DMU validation. So you try to digitally create the kinematic motions and then understand the inertial effects, all the forces required, reaction forces, all the stuff. Then comes the final stage where you do the design review management. So these were the recaps of day 4. So we'll enter into today's agenda, where first half will be handled by me and then second half will be handled by Mr. Narendra. So I'll be taking you through these topics, where digital validation introduction and then digital validation complementing technology adoption, and then considering quadcopter as a basic example just to illustrate. I'll be illustrating you about the 3 stages which are meant for any component which has to go through this FEA cycle. And then we have some question and answers. Then I'll showcase some videos. So with that, I'll close today's session. Okay, and tomorrow's session will be handled by Narendra. So digital validation introduction. So we are in this digital validation stage where basically our concentration will be on the structural validation, material selection, optimization, and then interpreting the validation done to freeze the final model. Okay, once we do this, the next stage is where you have this production concepts where manufacturing comes into picture. Okay, so all the other stages earlier to digital validation is where you do everything in a digital format. You also try to validate in the digital format itself. So the example for today's session being drone, what generally we want is that the objective is to have the drone lightweight and it has to have increased stiffness and the strength should be very high, and and the flight duration is also an important stuff. Why flight duration is important and why lightweighting? So these two are like related together in the sense, if you have this frame as very heavy, then your flight duration will also come down. So what this is very important. You need to see that you optimize your frame such a way that the stiffness of the frame gets increased. At the same time, the flight duration also gets increased. Added to the mass of the frame, you also have payload. You have the weight of the battery. You have the weight of the 4 motors, propellers, and all the stuff, which everything together comprises in drone. Okay. Okay. First, I'll just give you a brief introduction about the birth of the FEA. So in 1880s, in 1800s, John William Rayling, they started with natural frequency for simple structures. Okay. So the first analysis which was done was basically on a natural frequency, and thing is that natural frequency was one of the basic analysis which could be even done on the paper using equations, but for simple structures. But then later, what happened is that when the structures became complex, the more number of equations which were supposed to be solved, they became complex, and it required more amount of time to be spent, and that was an hectic job. So then what happened is that there came in a new method known as, the numerical method was developed, and basically that was again used for frames and trusses. Frames and trusses are nothing but the picture that you see on the right side bottom. You have a kind of frame where you have trusses. Okay, so that is what is a frame and truss. And then slowly what happened is that as a time, as there was progress in technology, 1943 we invented this digital computing. Again, when digital computing came into picture, it was not something like based on ICs and what are the electronic components. It was purely based on this vacuum tubes. So the size of the computer was, of course, room sized, and that was developed and commissioned by the US Army, basically to calculate the ballistic trajectories for World War II. Okay, and the amount of time taken for each calculation was, even that was better than what humans can do. Okay, then in 1950s, analog computers had been developed to process more complex structural problems. So with the promise of more powerful computers, analytical methods were advanced to include matrix based solutions of frame and truss structures. Still we are stuck up in frame and stress, but then mathematically this matrix method was brought in, and then we started using computers, but which were fast for that time. But today if you see, we we solve on in larger core, and then we try to even complete a car crash analysis within a time period of, let's say, 5 to 10 hours. Okay, next, then the next significant step was taken by Boeing in 1950, when they used this triangular stress elements to model wings. Okay, so it's nothing but they are the one who try to mathematically bring in this elements and nodes into this FE. Okay, so this is where, and this is how the basic concept of finite element was thus born. So next advancement was done because of NASA. So what NASA did is, like, they went to a company where they wanted, who were already developers of this FEA code algorithm. So they requested that, okay, you give us this kind of codes which can solve the linear problems for us. So they actually went to MSC. So hope you know MSC as a company. So even their products. So they started creating this algorithm known as Nastron, which basically addresses all the linear structural problems. So then in 1960s, they saw the true beginning of commercial FEA as a digital computer, replaced analog computers. Then what they did is, in late 1990s, the PC platform became a major force in high-end analysis. Models with 1 million degrees of freedom were being run on a desktop kind supercomputer capable of running 1 trillion operations per second. Okay. So coming to this digital validation complementing technology adoption. So how industries are using this particular technology. So I will explain you in further slides. So first, let's understand, like, what are the different types of analysis or the different types of validations which generally a company does, or any company does. Okay, so we have something known as static analysis, where again it is classified into linear and then non-linear. Then there's one more thing known as dynamic analysis, where it is known as explicit in terms of FEA. And one of the example I would say is an explosion or a car crash analysis. Then comes into picture is a thermal analysis, and under thermal we have heat transfer, we have thermomechanical analysis, and we have other different analysis like linear dynamics, geostatic, fluid, topology optimization, fatigue, buckling, and contact. So I'll just give you one small example for each and everything. So coming back to static analysis, if you see, there's something known as linear. So linear is nothing but we are going to consider that the material is going to behave in a linear format, though the material might have a nonlinear curve also, but then we are going to just consider up to the yield point. So that becomes your linear analysis. And if nonlinear comes into picture, that means I'm going to consider the complete curve or the stress strain curve of that particular material, where I want to predict the failure even at the last stage, which is nothing but the ultimate. Okay, I want to push my model or the design, whatever I have done, which consists of XYZ material, which has this nonlinear curve, and then I want to push it to till that fracture. Okay, and then comes this dynamic analysis, which is nothing but, let's say, I want to design a bulletproof jacket, and then I want to simulate it. So every time I can't, I can't risk someone's life, or I can't set up and then try to conduct this analysis. Instead, what I can do is I can create a 3D geometry, which is same as that bulletproof jacket. I can have in bullet, and then I can give it an high velocity, and then understand what happens to the bulletproof jacket. Okay, so this explicit is mainly how it is different from static analysis. When it comes to explicit, it is purely based upon the time factor. Okay, but in linear, there's nothing known as time factor. But when it comes to explicit, it is purely based on time. So car crash analysis is one best example, and even I would say airbag is also one a good example for explicit. Okay, so which is dependent on time. So within this much of milliseconds it has to function, or within this many seconds it has to go and impact. So I want to see like what happens if it impacts for a period of 2 seconds. Okay, so this is how we study this explicit. Next comes the thermal analysis, where generally any electronics, if you see it, basically heats up, and then you want to find out how the heat has to be dissipated, or let's say because of that heat, what are the components which are getting expanded or contracted, what are all those stuffs are taken care here. So conduction, convection, and radiation are also a part of this thermal analysis. Next comes linear dynamics, which is nothing but frequency based analysis, where resonance is one important factor which needs to be considered in every automotive or every moving component or anything where you have a rotating member. Okay, and next is geostatic, which is nothing but soil. So it is related to civil and structure. So that is what is geostatic. Next comes fluid. Fluid is nothing but we have something known as SPH, smooth particle hydrodynamics, and then we have something known as CEL, which is known as combined Lagrangian equation. So with that we can create fluid, and then we can do some simulations. Next is topology optimization, where you have a component. You have let's say you consider a lower arm of an automotive. So the weight of that particular component, for example, if it's 10 kg, I would like to go with topology optimization. I would try to find out which are the zones which are not actually participating in the transfer of load, and then that particular zone which is not participating, or it's not contributing to the stiffness, can be removed. So that is how you try to make an organic shape, and then that becomes your topologically optimized shape. So best example is our human bone. You can just try surfing online on this topology for further information. Next comes is fatigue. All these analysis are kind of cycle, where fatigue is one most important stuff, where let's say you have a component which is highly stiff, but then you have even optimized it, and then you have even considered, again you have run an analysis, or let's say you have done a DOE study, and then you have achieved a final design which you feel that it is very much safer and very much durable. But then when it comes to fatigue, what happens is that any automotive component, if you consider, let's say, a brake pedal or whatever, So we generally try to apply too much of force on the brake pedal. So it is designed for that with some amount of factor of safety. But then what happens if you apply the same amount of load 10,000 times? So if you see what exactly happens is that there'll be a small amount of crack which can initiate from some random point based upon the stress and strain. So that's how the pedal would fail. So this is applicable for each and every component, even the chair on which we sit. So that is designed for, let's say, 200 kgs. Though we weigh 80 kg, but if we try to sit and I mean, if we try to sit some 10,000 times, of course, the chair which can take 200 kg will even fail with 80 kg at one particular duration. So that has to be kept in mind. So that is how we generally approach for fatigue to get number of cycles as the final result. Next is buckling. We generally know any structure which is three times, I mean, in length when compared to its diameter or whatever, it would generally tend to buckle. So we can't have a structure simply without external supports, which is too high. So that is not recommended. So buckling comes into picture, and then we have again contacts. So all these analysis, when done as an assembly, contact comes into picture. Okay, that is very important. So FEA is generally highly stable when it comes to contact, when it comes to all three types of nonlinearities which are available. Okay, so generally in an industry, how do they do? So we have this CAD block which you see. So from CAD we receive the 3D models. Maybe that can contain the final, I mean, the GD&T data or whatever, but those things will not be considered here. It is just in geometry for an FEA software. So what FEA does is that during the pre-processing stage, we have something known as meshing. So all this CAD data is converted into a proper mesh. So then we have a criteria known as mesh quality, mesh convergence. So all these things are done in the pre-processing stage. So I do a pre-processing. I try to apply the amount of load which is required, and then I understand the functional behavior of the component, and then try to fix the regions where it has to be fixed. Okay, I do all the stuff and then try to run an analysis. With the result, whatever I get, if I'm satisfied, that's okay. If not, I can ask the CAD engineer to make changes to the component. It could be like increasing the diameter, or let's say I would request them to remove the chamfer or whatever it is, whatever options available. You can add material, remove material, and then redo this process. So with respect to the Similia Abacus portfolio, if you see, we have Abacus for FEA, advanced FEA, and then we have FSA for fatigue analysis. Then we have Tosca structure for the optimization. So this itself becomes as a cyclic process, which can be taken care by software known as iSet, which generally loops all these three software until you get the final proper model which you actually wanted. Okay, so it will give you in terms of meshed model, and it will give you results in terms of numbers and colors, which is again done using this post-processing stage. So this is a general cycle. CAD to FEA, pre-process stage. You try to solve it, and the output comes to a post-processing stage. You try to understand the behavior or the physics, and if everything works well, then this cycle stops. And if doesn't, then you will have to go to CAD and then again a remodel, and then the cycle continues. So this particular slide is an very interesting slide where whatever I've told earlier can be connected here, and I will even explain. These are all industry examples. So the first image, if you see an yellow color surface where you see a can with a red color cap, and it is filled with some fluid. Okay, so Coca-Cola is one of the company who basically do these kind of analysis. So thing is just to certify or just to understand whether the cap or the sealing in the cap region is that okay or not. Okay, so what I'm doing is, let's say I carry some hazardous fluid inside, and by mistake I drop it from some 1 meter or 2 meter of height. It should not get spilled, or let's say the cap should be very much intact. So how do I do that? So that is known as a drop analysis. with CEL technology. So I have the fluid, I design the fluid inside, I will have this cap threaded, and then I'll try to drop from different angles and different velocities and different altitudes, and then try to find out the final output based on the results. Okay. Next, you see a aircraft skin where I just basically try to do a static analysis and try to understand that all the stiffness and everything is correct. Okay, so that the structure is intact. Next is again the similar kind of drop analysis where we have a mobile phone. So I try to drop it and then try to understand its failure. And one of the most advanced analysis I would say is this car crash analysis. So I have this car traveling at an particular velocity, and then straight away it hits on a rigid surface, and then I can go and measure the kind of energy absorbed by the chassis, and I can even try to see there's a plugin which can even help you to simulate the mannequin. Okay, so I need not to have a dummy inside, and then try to connect sensors, and then try to take all those outputs. So that is a very costly process. But then when it comes to an FEA, we have that plugin. We can use that plugin. You can create a mannequin, and then you can say that these are the points of interest, and then try to get all those results. Next, you have a turbo machinery where you want to understand the motor dynamics, rotor dynamics. So all those kind of stuffs can be done. You can make the rotor to rotate at let's say 10,000 rpm, and then understand what happens to the blade at the macro level. Okay. Next example I would say is a stent deployment, where it is a highly non-linear problem where the stent is implanted into a human heart, and the size of stent is will be very much smaller. So it will be actually placed inside, and you will have a balloon kind of thing which will expand the stent, and this stent will I mean the orifice of the nerve will be expanded, and it will try to maintain that shape. Okay, so this stent is also supposed to take the pulses which are created by the heart, and the blood flow will also have that pressure, so this stent will also take care of that. Next comes another medical application where you see a bone marrow, and there was a time where let's say if the bone gets fractured, generally what at that part of time the technology was that we used to have steel plates, and then we used to screw, and then we used to go through a certain period, and then later we need to operate again and then remove all those foreign materials. Okay, then later after advancement there was a stage where you can use you can keep the material inside the body, and you need not to have so many screws inside. So but if in case it's disturbing, then we can go ahead and remove. If not, we can just leave it inside. And now the current technology is that based on I would say based on the shape of the bone or the kind of fracture, you can go ahead and design an implant particular to one patient, and then try to do that. And the amount of material which was used earlier is not used now. So we try to optimize it and then do all these implants. So next comes is sloshing analysis, where this is again a CEL technology. Basically, in any aircraft, if you see the fuel which is stored under this wings, so that has to be kept very careful, that so that the aircraft remains balanced. Whenever the aircraft tries to roll or yaw or pitch or whatever it is, this fluid will create an extra inertia effect onto the aircraft. So to dissipate the energy which is produced because of sloshing has to be taken care. Okay, so even these kind of things can be done. Next, you have a tire which rolls on fluid, which is nothing but hydroplaning. So how do we simulate it? Again, we have co-simulation options here. We have a tire as a complete rubber material. We can give the hyperelastic properties, and then we have this fluid which is nothing but CEL. And I have the threads on the tire where I can understand, okay, how does these threads help the fluid to spill away so that the rubber patch exactly comes in contact with the tarmac. Next is the highly advanced topic, which is nothing but carbon fiber particles, or let's say composite technology, all this stuff, where you can even give the failure factors to the composite and then try to understand the delamination factor. So there are a lot of things when it comes to composites. So composite related analysis can also be done. Next is seat belt analysis. So car occupant and this SRS technology. So all this stuff can also be simulated here. So using our simulation software. So then you have earth mover machine, which is nothing but it is a kind of a multi-body dynamic simulation. Even that can be done. We have nuclear power. I mean, the cylinder kind of stuff is nothing but a wall which actually covers that nuclear reacting core. So it's basically speaks on the thermal part. We have mobile phone. Again, you can consider that it's a drop analysis or a thermal analysis. We have this power plant heat exchanger. We have even the plastic clip is nothing. I mean, it's nothing new to you. So even this plastic clip is supposed to undergo a kind of tremendous FEA testing, where once you do the locking and when you try to open it without pressing those two button kind of stuff, it has to sustain that load. Okay, so it's one very good example. So if you see out of these examples, car crash analysis is a kind of explicit analysis. CEL analysis, where you see the water sloshing, is also an explicit analysis, and the phone dropping is also an explicit analysis. And if I say the bag clip is a kind of static analysis, thermal analysis falls under that static criteria. You have highly nonlinear behavior when it comes to stent. And then let's say you have composite delamination, which is also an again highly nonlinear process. So with the earth mover, if you see, it is an highly nonlinear with respect to the kinematic stuff and contact stuff. Okay, so the earth mover, we are not just going to see how it is going to function, but then we can also study how much amount of soil it can grab, and all those things can also be studied here. So I have an very good video for you. So I'll be also explaining on this video part. So these are the different types of analysis conducted using this Abacus and the 3D Experience platform simulation solution. Okay, I'll just play the video for you. So I think you are able to identify which car manufacturer has created these animations. So this is from Toyota. So just think about, like, if you had if you were not having this kind of FEA solution, then what you would have to do. So every car company has to dedicate some X numbers of cars for each and every test. So that would become really costly. So this is an aircraft crash analysis. So this is what I told you. This is known as SPH analysis, where you can even understand the amount of soil which gets loaded into the bucket is what going to create the stress. This is a kind of buckling analysis. So buckling analysis even applies to bottle. So this is the plastic clip which I told. So this is nothing but you have a gear pair, and you need to understand what is the kind of contact which is getting established. So this is to show you that how strong is the contact formulations within Abacus. So this is how a bullet would penetrate through a metal plate or a composite, if you want to check. Okay, this is nothing but I'm just trying to create a scenario where I have a wind as a force. And this is nothing but let's say we have a battery, lithium battery, and what happens if it starts to swell. This is to show you the capability of the fluid thing which we can create using our solution. So this is an highly viscous fluid. And this is nothing but, let's say you can take it in two ways. This is the fracture propagation. So from where does the fracture propagate? How it would propagate? This is again a kind of thermal analysis between multiple layers. This is nothing but an transient analysis, thermal transient, where I do a welding process and then try to understand. So the heat generated by the welding, how it is going to affect my component. So this is to show you that how good is contact. So, and how important is contact. So these are known as explicit analysis. Whatever you saw till now is what is known as explicit analysis. So this is an rubber band kind of stuff, which is hyper elastic in behavior. So I try to rotate it, and then once I mean, if I remove that boundary condition, the energy stored in the rubber, of course, tries to rotate the other end. So again, it starts to wind up because of the inertia carried over by the blades. Hope the video was very much interesting. Okay, now coming to this optimization stage. So this is very much evident if you see nowadays most of the car manufacturers, for example, BMW, Audi, all these kind of big chains, what they are doing is that they don't go with the normal shapes. They are trying to come up with complete organic shapes which are weightless, but then 10 times or 20 times stiffer than the normal structure. So you see to the left side top, you see a picture where you have a normal design, and then you also have a design where you see which is completely optimized, but the function remains the same for both the designs. Same way you have another example to the right side bottom. But the difficulty of this particular thing is that these kind of components can be either fabricated using casting process, or you will have to rely on this additive manufacturing technology. But then with the commercial machines, let's say with the lathe and other machines, it is not possible. But 5-axis and more than that will of course help in fabricating these kind of components. Okay, so next I want to showcase you what are the different stages of optimization. So we have this particular clamp to the left of the screen. So that is a normal clamp, which you consider that it weighs somewhere around 1.5 kgs. Okay. Now, what the additive manufacturing software or the optimization software, which is Tosca, and when it comes to 3D experience, it is known as the GD role. What they do is that once you feed in this particular 3D data and then say these are the points where we generally fix, and this is the kind of load which is going to act, then the software would try to run multiple iterations, and then it would try to find out which are the elements and nodes which are actually not participating in the analysis. So then it will try to slowly remove those, and then it will end up, so we end up with a final a shape which you see to the right side extreme. You see a shape which is kind of an organic shape. Okay, and then we also need to use CATIA and other surface tools using which you can try to create a proper organic shape, because whatever the shape which you get out of this FEA tool or the optimization tool cannot be directly manufactured. You will have to create it little bit symmetric, and you need to make some adjustments. So we do some post processing onto that. So this is the kind of stage which is followed, or this is how a component has to go through when it comes to optimization. Okay, so these are the other examples which I would like to showcase. So you can predict it by yourself. So you have to the left, you have a component where you have the most optimized shape, and which is printed using this additive manufacturing technology, metal printing. Okay, so this is a metal printing component. So the benefit of metal printing is that whatever the material you want, you can select those metal powder and then do the printing. Though it is a time consumption consuming process, what happens is that the final product can be directly it could be put in use. So you need not to again do multiple iterations. Let's say you first do print in plastic and then try to create a core and cavity, and then you try to put in some other material. So that kind of process is not required here. You straight away have the 3D geometry, give it to the optimization software. You give all the kind of boundary condition, do the FEA, everything is done. Then you get the final shape, give it to the machine, and then it will give you the final. Uh, uh, I mean, the most optimized print, which can be directly used to the assembly itself. So I have another video for you. So this is on the optimization part, where I showed you one image, like how a normal design is getting converted into the most optimized. So this is our 3D experience platform, where we do all these kind of optimization. So this particular module, to the left side top, if you see, there's a compass, and next to the compass, if you see, it is CATIA functional generative design, where you load in all the 3D parts, and now you start up with the pre-processing stuff. So it's nothing but I try to assign a kind of material. Generally, I mean, let's say it's a steel material. Okay. So I assign material, and then I mean, I create all the GD&T related stuffs. Okay, and I say these are the joints which need not be considered for the optimization, because these are the functional regions which are very important. Okay. Then what I also do is that I try to do a basic simulation. Okay. So when I do it, I also need the contacts, which are very important for me. Okay. So when you I mean, when you start using contacts, you also have an option on a slave and master. So all those stuff. So now it is a stage where I need to I mean, say that, okay, what is my target? So how much weight reduction I need to do. So we have different materials. So we try to I mean, we try to set the targets. Okay, and we try to get some results out of the FEA. So this is the result which you generally get out of an FEA, and this is also the optimized result. So if you see, this shape cannot be directly used for fabrication. It will not be much I mean, aesthetically good, but then you also need to consider the manufacturing capabilities, or let's say feasibility of manufacturing. So what we do is we try to study this component further, and then try to I mean, bring into an this CATIA module again, and then try to construct proper shapes. In the sense, I'll be giving it a proper smooth shape. So I mean, I'll create this kind of organic shape. Okay, it would already give you the organic shape, but then we need to create I mean, aesthetically a good shape, as well as it should be feasible for the manufacturer. Okay, so I do all this stuff, and then end up with this final part. So wherever you see a void, okay, wherever you see a void on the screen is the amount of material which we have saved. Okay, but the function remains the same. The factor of safety, all the stuff remain the same. So this is how basically we do an FEA analysis, and then we try to optimize based on the FEA analysis. So legacy is nothing but the normal component, and then the additively manufactured. And the same, you, if you don't have this additive manufacturing thing, then you can go with the machining. Okay, so coming to this quadcopter as an example. So the description of on the physics and the types of loads, vibration, aerodynamics, thermal. So these are the kinds of things to be considered. So when it comes to physics, if you see, all these rotors will rotate at some high RPM, and these rotors have to rotate diagonally in opposite direction, so that what happens is it stays balanced. Okay, if not, it can't fly actually. Okay, that is why the rotor blades will always rotate in different directions. So next, the types of load you need to consider for an analysis is that battery is a kind of load, the electronics are a kind of load, and then the thrust which is created by these rotor is also a kind of load. So these things to be considered for the design of the arms. Okay. Next thing is that when all these four motors rotate at variable RPM, of course, what it does is that it would create a kind of vibration. Okay. These vibrations are these vibrations are caused because of let's say the availability of air and velocity of air and density of air. So all these things contribute to this vibration. And let's say if the rotor is not good, or if there's a fault in the bearing, or let's say there's some other factor which would, let's say the payload is too much, or whatever it is. So all these things will cause vibration. Okay. So this vibration also to be considered for this analysis, because resonance is one very crucial component to be considered. If you don't consider it, then of course the fatigue life would come down. So we need to take care of that also. Next is aerodynamics. So as of now, this drone is not that much of aerodynamic, but then if I try to create an coupe kind of stuff on top of the center body, then what that would do is that it will try to reduce the drag which is created by the battery and electronics and all the other stuff. Next is the thermal, because the drone batteries generally have high discharge rate, and because of that high discharge rate, what happens is that lithium battery would generally tend to heat up. So when I try to cover it with this aerodynamic coupe, I should also consider that battery is also considerably cooled. So that is very important. Okay, so generally, you know that these are the different components which together form a drone, which is nothing but you have four motors, which are brushless motors. You have something known as an FC, which is nothing but flight controller. You have a lithium polymer. You have a carbon fiber frame. You have radio signal transmitting antennas for both receiving and transmitting. Okay, so then you have a gyroscope and accelerometer. You also have barometer. So all these stuff which are ready-made available in the FC itself. Okay, so that is a main computer of the complete drone. So considering all these steps, whatever I had explained in the previous two slides, now coming to the design of the arm. So what we do here is that we first need to compromise on all this stuff, and then come to a conclusion that, okay, I'll go with aluminum, or I will go with carbon fiber, or I will go with some kind of different kind of composite, or do I need to go with let's say kind of a plastic, which could be an ABS plastic. So it all depends upon the function what this drone is going to do. So how much load it is going to lift. So what if in case if it falls from some 10 meters of height, it is supposed to sustain that kind of impact. If it is completely damaged, then rebuilding this drone is again a waste of money, waste of time. So all these things are crucial things are considered. So what we do is that we do a lot of material study. Once we do the material study, we also need to find out how to lightweight. And at the same time, when we do the lightweighting, of course, what happens is that whenever you do lightweighting, there's a decrease in stiffness, but then we have to bring in other few factors which would help us in increasing the stiffness also, which is nothing but by adding some kind of stiffness, or let's say by creating a hole, or let's say you have some other kind of material which can be bought inside, or you can create sandwich of multiple high stiff materials. So there are multiple factors which can help you in increasing the stiffness. Okay. Now, when you open the software, the first stage generally is known as a pre-processing stage, where you try to collect all the data which were explained in the previous three slides. So the first point is collect all the data. try to understand the function of this particular arm, and then what you do is that you try to create a model in a 3D modeling software, let's say CATIA. Then that model is imported into your FEA, which is the pre-processing, the basic thing, which is or the first step, which is done in the pre-processing. Then you go and create the material model. The material model basically consists of information, which is nothing but the stress and strain curve. To the right side, if you see, this is one very important thing to be considered, without which there is no material property. So material property generally has this complete stress strain curve. So this is very important. Next, what you do is that you need to find out, okay, which technique would help you in validating this particular arm. Will it be in explicit analysis, or it is going to be a static or an implicit or a thermal, what it is. So you need to understand, okay, if it's an impact analysis which I want to perform, then of course I would go with an explicit analysis. But then if it's an structural validation where the arm is going to be static, and then I just want to consider the thrust as the force, and then try to apply it, and then understand, okay, how much thrust can my arm withstand. Okay, I mean the drone arm can withstand. Okay, so all these things come inside boundary condition and loads. Next is meshing, which is very important. So meshing is nothing but the same truss and the structure whatever I spoke in the first 2-3 slides. Okay, the formula remains the same, but then today we have more number of degrees of freedom. So we do the meshing here. So what actually meshing does is, once you do the meshing, there is no connectivity between the 3D model and the analysis. What happens is that the 3D model is morphed using this nodes and elements. Okay, so understand, nodes and elements will take the shape of the 3D, and from then there is no relation to the 3D. Okay, so 3D model is just an outline for the meshing module, where the meshing will try to consider all the boundaries, and then it will create a meshed model, okay, which consists of nodes and elements. So hereafter, the material property, the formula or the matrix and stiffness matrix, all those things, they sit on this mesh. Okay, it is based on purely mesh, not on the 3D. Though it is a morph data, so meshing is very important. Okay, if you don't do a proper mesh, if you don't validate your mesh, or if you don't take care of convergence of mesh, then of course the result that you get will not be a proper result. So that is also very important. Okay, so there are multiple criteria where, let's say, one criteria which generally people follow or the engineers follow in industry is that if you have a thickness, then you see that you have minimum of 3 layers of meshing. Okay, so if you have a hole, then see that how accurate the hole is mapped by the mesh. So if you don't consider these kind of factors, then of course we end up with multiple results, then we will not be able to validate. So this comes by experience, and the next stage is that you fix the arm at one of the end, you apply the boundary condition, you do the meshing part, and then what you do is that you try to solve it, to push it to the solver, where solver is nothing but basically a ton of algorithm, where it consists of mathematically this differentiation equations. So it tries to solve for each and every node, and then tries to find out the equilibrium for each and every equation. And if this equilibrium is satisfied, it will go step by step, it is known as iterations, and then you end up with the final result. Okay, so this is where you tend to lose some of the accuracy. The reason is that there are some roundings of value, or let's say for the previous equation it would be 2.8, and the next equation would consider that as 2.9, and then it would proceed. So a few of the decimals will not be considered. So that is how a little bit of error is also a little bit of error comes into picture, but then we can try to resolve it by doing some settings in the software itself. So when coming to meshing, because I had stressed on the meshing part, meshing is very important. So meshing is nothing but you are trying to break a geometry into known shapes. Okay, so what happens if you try to break it into unknown shapes, you will not be able to calculate the area, volume, and all those stuff. Okay, so what you do is that you try to break it into known shapes, but then you also see that the shape is also maintained, in connection with the 3D. Okay, Generally what happens is that when you create a coarse mesh, that would never match the actual 3D, because there are few places or few areas which will not be where the mesh will not be able to occupy those places. Okay, so that is where you will have to refine. So this is also one of the factor which contributes to little bit of inaccuracies. Okay, so we over a time, by experience, you will come to know that okay, so if this region is supposed to be mapped by a mesh, then what you are supposed to do. So there are like tet element, prism element, pyramid, hex element. So there are multiple elements which are available. Okay. So when it comes to complex shapes, if you see, what happens is that we have this option known as tet element. It's a kind of pyramid with three. You will not have four uh, vertices, where you have only three vertices. So tet element is majorly used for shapes where you find the geometry is very complex. Okay. Okay. So coming to Q&A, I would like to just uh, get the answers for these questions. There are hardly few questions. So which type of elements are basically used to mesh complex shapes?
I would like to answer the question.
Okay.
I think that element is used to make the mesh complex shapes.
Yes, you are right. So tet element is one element which is generally used in areas where you find you're not able to do the hex meshing. Okay. Generally, people will not prefer, the engineers will not prefer to go directly with the tet. They will just try to break down the model into hex as far as possible. And in the regions where it is not possible, then we go with the tet. And there are some geometries where tet is the only option. Then we can, of course, go with tet also, not an issue, but then we always need to consider whether the tet has to be first order or second order. So these are the technical stuffs which are inbuilt. So this one more thumb rule, like second order tet mesh is always equivalent to first order hex mesh. So you need to also consider these kind of thumb rules when you do an analysis. So option C, if you see, is mentioned as hybrid element, which is nothing but combination of both the hex and tet. So even that could be an answer, but then the relevant answer is whenever there's a complex shape, we generally try to finish the meshing using tet elements. So the next question is that what kind of behavior will a brittle material possess? So this is something related to the stress strain curve. Okay, so I would like to hear the answer from you. And
Linear?
yeah, so it's linear. So why not non-linear? Okay, so thing is, a brittle material generally, if you see, you try to apply the load, and material would try to withstand, and all of the sudden after the yield, the material will never try to enter into the plastic region. So plastic region is where your material would try to bend, and then it will keep bending. Okay, it will not come to its original shape. So when it comes to brittle, better example is that you consider a glass. Okay, so window glass, or what are the glass panel, or let's say even cast iron. So these are the materials which can take heavy load, but then once the failure happens, or let's say once the load increases, then they will not be able to hold the weight, and all of the sudden it will tend to break. Okay, it will try to shatter. So this is the behavior of a brittle material. So the behavior of a brittle material with respect to stress strain curve is always linear. So linear is the right answer. Okay, so as I told you, we completed the pre-processing stage where we assigned the material, we did the geometry edits, we did the meshing, and we given the boundary condition and all the stuff, and then we have given it to the solver. So in the solver, what we do, what we request to the solver, we ask solver, okay, you solver, what you do, you give me the contact pressure at this particular area, and also what I can also do is I can say, you do one thing, like you also give me the displacement at this particular zone or this particular set of nodes, and I want to see the kind of whatever the displacement or reaction forces or whatever. Those kind of requests can be asked to the solver. Okay, next is that how do I want to solve the problem using the hardware which I have. So these settings are available when before, in the user interface, or even through the command lines, you can do this. So CPU is nothing but the processor which we have, which is Intel Core i7 9th gen, 10th gen, or Intel Core i9 or Xeon processor, all the stuff. So, and then next you have something known as GPU processing, which is nothing but graphical processing, where you have NVIDIA and AMD cards, which will also have something known as CUDA core, which will also help you in processing your problem. Okay. So next is that there's something known as convergence. So when you try to solve any problem, you should always take care that your problem also gets converged. So that is nothing but I told you that each and every equation should attain the equilibrium. If one of your equation is not attaining the equilibrium, the reasons could be the model error, or mathematically it is not possible. So to make it possible, what you need to do is that the mesh quality, and there are multiple factors which come into picture. So there are multiple settings also. So you will have to play with all these things and then try to converge your solution. So then you once you do all these things, you try to submit it. Okay. So convergence criteria becomes an input during the solving stage. Then you try to submit your job. So in the post-processing stage, what happens is that on the screen you try to see multiple colors. The band would be from blue to red. That doesn't mean that red is the portion where it is going to fail. It just says that blue is the portion where you have the minimum value, and red is the portion where you have the maximum value. That maximum value could be after yield or within the yield also. Okay, so it is just a kind of representation which makes us easy to understand and then easy to predict the exact zone where we need to concentrate. So you get these colors matched with values. It shows the one measure stresses. So I see that somewhere around the meeting point I have high stress. That is the zone where I need to concentrate. So what and all I can do using the post processor. So using post processor, I can do the probing, which is nothing but I can go at node level and then understand how much is the displacement, how much is the stress, which is carried by this particular node. Okay. Then what else I can do is I can try to plot different graphs. Let us say it could be a stress versus time, strain versus time, or else reaction force, or load versus displacement. So there are multiple curves which can be plotted. So then next comes is sectioning. I can section this arm into exactly in the zone where I need to concentrate. I can section it over there and then go inside the mesh and then understand what else can be done. So that is there. And again, report generation is one of the options. So basically post processing is all about the report generation. Okay. You can either create it in terms of animation, or you can create it in terms of static image, just to to forward it to the next level of a team where they do the validation by seeing your report, and then they come up with a best solution. Okay, so then we have other options which are known as scaling and all those things. So this particular image explains on how I started and then how I ended. Okay. So to the left, if you see, this is the first arm which I selected, and then I tried to apply load, and then I found, okay, there's a chance for me to optimize this arm. So I tried to remove some material in that fashion, which is the second from the left. And then what I again did is that I again tried to remove a few more material, but then that did not help me. So that I had to attach a stiffener, which helped me little bit, but then that particular shape, if you see for some reason, let's say for vibration or some other reason, it was not convenient. I was not able to take the electrical cable through that stuff. So what I did is that I went and then tried to add a channel kind of stuff where my cable remains safe. Okay. So then later I understood, okay, having those holes were of not much use. So I removed, because if I have these many holes, of course, I'll have to spend more time in manufacturing also. So all these kind of things to be considered. Okay. So then I came up with another iteration. Again, I tried with another iteration. So then finally I found that, okay, if I had some holes, of course, it is going to reduce some material. But then the kind of stiffener which I've used has, of course, increased the stiffness of the arm. So this is how we will have to do different iterations. So we end up with a final. So you just need to focus at how was the first drone arm, and then what is the final drone arm. Okay. So this is the same picture from a different angle. So the hole which you see at the place where the motor would sit is just to have this wire routing. So day two, which will be handled by Mr. Narendra. Of course, he will concentrate on the main frame where contact comes into picture. You will showcase or illustrate on the contact part. Okay, so next I have one more question. What type of analysis procedure to be selected for a crash analysis?
I think it is thermal analysis.
Okay, if you see the question is crash analysis. So crash analysis is purely based on time. So if you see out of the given options, thermal is basically on the heat, okay, heat energy. So when it comes to crash, the right answer would be explicit. Okay, so explicit is the kind of analysis procedure which basically deals with crash analysis, drop analysis, all this stuff, all these kind of time-based analysis. So static, as already told, it's nothing but you have the drone arm, or let's say you have the connecting rod of an engine, or you have the chassis of an vehicle, or let's say you have a civil structure where you have the structure, you fix the structure, and then you try to apply some amount of load considering the stress strain curve. It could be linear or non-linear. Okay, so that becomes static. But when the same structure is there, let's say you have a 10-story building, and then you want the structure to undergo a seismic analysis, you want to find out how the structure would behave, then that doesn't become static, that becomes explicit again. Okay, so buckling is, of course, if the structure is too huge and if there are not much supports, then I would say the structure would buckle beyond the once it reaches the buckling load. And coming to buckling, there's one interesting thing which I would like to put forth is that I showed you a bottle example where they try to compress it and then understand, okay, the bottle buckles at what load. Okay, now one live example I would give you is, I would like you to think about this. You have this Coke bottle, and this Coke bottle will have a kind of different shape at the bottom. Okay, so there is one particular reason why we have that kind of shape, why it is not flat. Okay, so that particular shape will address a issue. So that is the reason why they have that shape. So you can try to, I mean, do the research on this particular shape of a Coke bottle, or any I mean any cold beverage bottle, Coke or Pepsi, Fanta, or whatever it is. You just try to figure out why we have, but there's something related to this buckling. Okay, so I have one video for you. It's on the simulation of our sustainable innovation. So if you see, I mean, throughout the globe, logistics is one very most important stuff. Okay, without which anything which is fabricated or whatever is done in an industry, that doesn't reach us. So to make these stuffs reach us, we of course rely on kind of transportation. Okay, it could be all these modes of transportation where you see one thing is common, which is nothing but the crankshaft, the bearings, and all the stuff. So these generally help us in international trading. So we need to see that the crankshaft which is there, and the ocean which is highly dynamic. Okay, ocean is never the same every 5 minutes or so. So ocean being highly dynamic, the engine of the ship is also supposed to have that much of durability. So how do we do? So we do this multi-body dynamic kind of analysis using the Simula Abacus solution. We try to find out the kind of stresses in the contact regions. We try to find out, uh, understand the fatigue analysis. Okay, we also see that, okay, if this is a region where crack would propagate, then how do I mean, eradicate it? So all these things are there. So factor of safety need not be too high, but then I need to also keep in mind factor of safety should be sufficient enough. So we have this DOE study. So we do a DOE study. We get a lot of data in terms of dots. So then I go and pick the right dot which suits all my requirement. Okay, so this is how basically an FEA cycle or a digital validation cycle comes to an end. Okay, so let's see what are the importance of design validation. Is that FEA is a crucial step that you can easily add to your development program. It will save time and money by highlighting problems and finding solutions during your product design phase before any material is ordered or before you even contemplate cutting steel. Okay, so check your design is on track during the design process. You check the calculations, and when hand calculations are too difficult, that is where you basically go with this FEA stuff using the digital validation process. Then we try to optimize stress, mass, heat, etc. to get the best results before manufacturing stage, and then understand the structural behavior. Therefore, we remove the most important line is that we always see forth that we try to remove the uncertainty which is there in the design phase. Okay, so thanks for your patience, and day two you'll be of course seeing other challenges which are there in the within this digital validation stage. So thanks everyone. Thanks once again.